Okay, so I'm going to be talking about Rosetta, which I spent several years working on, I'm going to be talking about the spacecraft itself, some of the challenges we faced, the background to the mission I'll do first by way of introduction, and why it's called Rosetta. And I will talk a bit about the UK experiment, which wasn't done very far from here, at the Rutherford Appleton Lab and at the Open University here in the UK. And then at the end I'll talk a little bit about what we discovered when it was there, and show you some of the pictures. Okay, so one of the things I'm going to spend a little bit talking about is the orbital profile, because this was so unusual for this mission, because he wasn't just going around the Earth or around Mars even. So the orbital profile is something that I'll be discussing in a bit more detail later, because that was so unique for the mission in terms of how the spacecraft was going to get there and some of the problems that caused. So Rosetta is named after the Rosetta Stone, which some of you may have seen in the British Museum. It's been in the British Museum for a couple of hundred years now. Napoleon's army found it, and then the British Army, I think it was, or the Navy possibly, returned it to the UK. One of those great Anglo-French tussles, which continue. Anyway, the importance of this was that it had the Greek, the Demotic, which is the ancient Egyptian language and writing, and then the hieroglyphs, all on the same tablet, so that the Jean-Francois Champollion and Thomas Young in the UK were able to look across these three parts of the stone and understand what the hieroglyphs meant for the first time. So this was, transformational in terms of understanding hieroglyphs. Now, why is that relevant to Rosetta? Well, the relevance is that cometary material is like a time capsule from the beginning of the formation of the solar system. So it's like it's locked in record of what the solar system was like at the start. And by understanding a comet, we can understand, perhaps to some extent, how the solar system came into existence and how it was formed. So that's the discovery analog, if you like, in terms of the Rosetta Stone. It's unlocking the secrets of the evolution of our solar system. Now, this comet, 67P, Churyumov-Gerasimenko. So Churyumov and Gerasimenko were the two astronomers who found the comet, who discovered it in 1969. 67P means it's the 67th periodic comet to be discovered. Halley is 1P, for those who are interested. And why was this comet, I'm going to talk a little bit about it on the next slide actually, why was this comet of interest? And it's basically a class of comets which have a short period, and by short period I mean 5, 6, 7 years. So these comets are not going out as far as Halley's Comet. Halley's Comet has an orbit of 67 years, so much, much bigger. And these comets have basically been captured, and they go around the inner solar system. They go out as far as Jupiter, and it's Jupiter that's brought them into this part of the solar system. And what does that mean for us? Well, it basically gives us a comet which has a low enough energy orbit that we've got the chance of doing a rendezvous with it. Not just a flyby, a rendezvous, fly alongside it, put a lander down. So Rosetta's main goal was to look at the cometary nucleus from a close range and study the environment as it got closer to the sun, the coma and the tail and so on. So rendezvous was at about 4 astronomical units from the sun. I need to explain astronomical units, so I'll come back to that. Through to 1 astronomical unit, which is the closest the comet got to the sun and when it's at its most active, and then flying out to about 2 astronomical units. And on its way in that elliptical orbit, it would pass through the the asteroid belt twice. So there was a sort of secondary goal was to have a close look at some asteroids as you fly by past those. Now, an astronomical unit is the nominal distance between the Earth and the Sun. So that's like our yardstick for measuring things in space. So one astronomical unit, 150 million kilometers, give or take a bit. And Jupiter is at about just over 5 astronomical units in terms of your solar system meter or rule. So looking back on this, when did it all start? Well, it all started really in 1985, which is nearly 30 years ago now. Sorry, 40 years ago. Time flies. In something called the Horizon 2000 Space Plan, and this was all about the European Space Agency, ESA. You'll see that on a few slides, I'm afraid. European Space Agency and NASA, I guess you'll recognise. And they had 4 cornerstone missions, and Rosetta, or a mission to a comet, was one of those. It was the 3rd cornerstone. So this is when the thing came into existence, and it was the scientists who decided on the priorities. There was committees of scientists meeting in the early 80s and saying, well, what's important? What do we want to spend our taxpayers' money looking at? After that, in the late 80s, there was some studies that were done between ESA and NASA on something called Comet Rendezvous and Asteroid Flyby, which has a catchy name. It's about what Rosetta's ended up doing, so that's a good thing. But it was a much bigger spacecraft. It was a real monster. It was based on one of the NASA Mariner spacecraft, 6 tons, which is about twice the size of Rosetta, and it was a very ambitious mission. Even more ambitious was at the beginning of the 90s. There was studies of something called Comet Nucleus Sample Return. So don't just go to the comet, go to it, bring a piece back to Earth and analyze it in the laboratories back on Earth. And that's, as you can imagine, a very ambitious way of doing things. So, and that proved to be, again, too big, too expensive. So Rosetta, as we know it 30 years ago, came into existence in about 1993, when ESA approved it as a mission to go forwards to the sort of feasibility study stage. It would have a launch in 2003. It would have 2 landers, and you'll see on the back of this model, in fact, there are 2 landers. JPL in NASA the Jet Propulsion Lab would provide one of the landers, and the other lander would be provided by Europe. And this is when we began the studies involving industry, which is where I was working. So in 1995, I joined one of the feasibility studies that was done in Bristol in the UK, leading up to the selection of the prime contractor and the industrial team at the start of 1996, and the design phase for the satellite. And also the experiments on board the satellite were done at the same time. And in 2002, basically when the spacecraft was finished, that's when my involvement finished, when everything was built and prepared for ready for the launch. So why have we got an original launch date and a revised launch date, I hear you ask? Well, it's all to do with the launcher, nothing to do with Rosetta. One of the interesting things about this mission was that it had a fixed launch date in 2003, literally 2 weeks in that year, when the spacecraft had to be launched in order to get to the comet. And for the original launch, it was supposed to arrive at Comet Vertanen, not the one that we talked about, 67P. And what happens is, in 2002, we had the maiden flight of the Ariane 5 launcher, big launcher, Ariane 5 Europe, and it failed. Software error, again. And there was an almighty kerfuffle. The investigations problem understood, and then Rosetta even more not only needed an Ariane 5, it also needed an enhanced Ariane 5. It had to be a more powerful Ariane 5 than the usual one, the standard one. So in December 2002, there was a maiden launch of the uprated Ariane 5 launcher, and that failed, literally a month before the Rosetta launch date. So, as you can imagine, a month is not enough time to sort out a problem, and it was to do with the engine this time, the first stage engine. So there was a big effort needed on the launcher. That meant that Rosetta missed its launch date, which meant that we needed to find another comet to go and visit and another launch date. And it was about a year later. So what can we say about some of these? So I've just got a slide here comparing the two comets. So the first one, Virtanen, was a bit smaller. It's only 1.2 kilometers diameter compared to with the one we went to, which was about 4 kilometers. And that's a concern because the bigger the comet is, bearing in mind the lander is essentially doing a free fall from the mothership in orbit above it onto the surface of the comet. So the bigger the comet, the higher the gravity, the harder you'll hit the surface of the comet. So this was a concern, and there was an upper limit placed on the comet that the lander could land on of around 5 or 6 kilometers, I think it was. So this was at the upper end of that region. The orbital period was similar, 5.5 years compared to 6.5 years. So they're both short period comets. They were both doing a similar perihelion. Perihelion's the closest approach to the sun. Aphelion's the furthest distance you are away from the sun in the orbit of the comet. And they were both, close to the ecliptic, only a few degrees above the ecliptic plane. That's the plane that the Earth and the sun are in the solar system. So these comets were similar. The one we went to was a little bit bigger, so there were some concerns, but nothing untoward. So how did we choose the comet? Because when we were doing the feasibility studies in the middle of the 90s, there were about 12 comets, I think, we were looking at in terms of how do we design a spacecraft which could go to any of these. That was the sort of question we were asking ourselves. And the one that I mentioned already is the fact that they have to have be a short period comet. They have to have this orbital period of 5 or 6, 7 years. Another factor was, if we look at it with a ground telescope and it's not very active, that doesn't sound like a very interesting place to go. If it's not getting a lot of coma and gases coming off it. So the activity level was another consideration. And some of these comets some of them were more active than others. So going to a more active comet was one of the things. And from a spacecraft point of view, we needed to be able to cope with, have a way of getting to the comet, in terms of gravitational assists from planets and amount of propellant we could carry on board. So these were all considerations, and also how far away from the Earth it gets in terms of the communications, and how far away it gets from the sun in terms of the power and the thermal considerations. Launch delay was another factor. So if we left it 5 years, left the spacecraft sitting on the ground for 5 years, that's obviously going to be more expensive than if we can launch it a year later. And the 5 kilometer one I mentioned. So the bigger the comet is, the more gravity it has, and the more demanding it will be for the lander to land on. So these images are from 2003. So we were looking at this new comet, 67P. We had our spacecraft ready on the ground, and we were just looking for a new target. And these telescope images are from the European Southern Observatory in Chile, on top of a mountain in Chile. The scale on the right-hand scale, that's 100,000 kilometers, that white line at the bottom of that right-hand figure. The one on the left, you've got more of a chance of reading. That's 65,000 kilometers. But you can see in these images that you've got activity, particularly the one on the right. You can see it look like some sort of jets coming out underneath. So it looks, nice and active. The omens were good, should we say. And the other thing they could do was work out how from the when you look on this one, the lower left-hand curve, what you're looking at there is the amount of light reaching the telescope on Earth. And you can see it goes up and down. And that is telling you, or the way it's interpreted is that as the comet rotates, the amount of light because the comet doesn't generate any light on its own. It's basically reflecting sunlight. So not very much of it, only a tiny amount. So it's a very dim object. But from looking at the light curve, you can tell how quickly it's rotating. And that's what they used to estimate it had about a 12-hour rotational period. On this figure, it's got these red stars marked on and most favorable landing areas. And what this was on about is that if you're going to land on a comet, if you land on one of the mountains, as it were, one of the highest altitude areas, if you think of it in those terms, then the lander will be going at a slightly slower speed than it would if it landed in a valley further down, to have less distance to accelerate under the gravity of the comet. So that's what that means. Landing at one of the tops of a bumpy comet would be more attractive. So this is the shape that they were talking about in 2003, just before the launch. These astronomical measurements were done using the Hubble Space Telescope, in fact. So we talked about the comet. Now, how are we going to get there? So what I've got here is, and I'll explain the diagram. You've got a grid on the right-hand side of the picture, and the grid size is 1 astronomical unit. And you can see I've got sort of 2 on the left-hand axis. I've got 2 down to -6 on the y coordinates, and I've got -4 out to +2 on the bottom axis, the x-axis. So you can see the sun would be at 0, 0. I haven't got a pointer, have I? Which is in the middle of that circle there. So that's where the sun is, and then you can see a circle where the Earth is, essentially 1 astronomical unit in a circle going around that point. And then further out, you can see a dashed line, which is Mars, at about 1.6, 1.7 astronomical units. And you've got the comet, this solid line that's highly elliptical down here, this one. This is the orbit of the comet. So you can see it's going out as far as Jupiter's not on there, but you can see, it's about 5 astronomical units from the sun, and Jupiter is around there. So getting from the surface of the Earth around the solar system, what was the tour like? Now I've got the events on the left-hand side in this table. So let me just try and take you through that step by step. So first part of the mission is pretty straightforward. You launch in March 2004. You fly a little bit closer to the sun and then a little bit further away from the Earth, and then swoop past the Earth a year later and pick up some speed from the Earth. The Earth slows down very, very slightly, but not so much that we need to worry about it compared to a 3-ton spacecraft. And then the next leg is from the Earth to Mars. So we're going out to Mars this time, and we're flying past Mars a few thousand kilometers, and then back to the Earth. So we're now at 2007. So we're going past Mars in about 3 years after launch, and nearly 4 years after launch, we're back at the Earth again. But we've got one more fly past the Earth yet. In this leg, we're going out through the asteroid belt for the first time. So you can see that here, where that little dashed line is. That's the first pass through the asteroid belt, and a fly past of Steens. And this was at reasonably high speed. You know, we weren't able to stop and have a look. You know, we were on our main mission out to the comet. And then back to the Earth. So March 2009. So this is now 5 years after launch. So time's ticking away. And we still haven't done much science. We've been to an asteroid. And then on the final leg, we have our final flight past of Earth, out through the asteroid belt again, and visit an asteroid called Lutetia. And then we have a very interesting part of the mission where we have a big maneuver in OCM4, you see out here. So this is, 3 or 4 astronomical units from the sun. Big amount of propellant is burned on board. And this is to match our orbit to that of the comet. And after that's done, the spacecraft, and if you think about how quickly the spacecraft is moving, I mean, the comet takes, 6 years to get around the orbit. The spacecraft moving on this part of the orbit is moving very slowly at aphelion because it's so far from the sun. And it is put into hibernation, and I'll just talk a bit about hibernation later on. But this is when the spacecraft's basically put to sleep because you can't afford to operate it in terms of the amount of power you can generate on board. You're so far from the sun. You've got this enormous solar panels, but they don't generate much electricity out at those distances. So the spacecraft's put to sleep, and then in January 2014, not shown on this table, but in between the aphelion and the rendezvous maneuver, the spacecraft is woken up, or wakes itself up, which it did, fortunately, in January 2014. So this is nearly 10 years after launch. And then it's talking to the ground. There are some images taken of where we think the spacecraft doesn't know where the comet is. The ground has to tell it. So point your cameras at this bit of the sky. The spacecraft does, take some images. They get sent back down to the ground. And then the controllers on the ground work out, okay, so we need to do our final maneuver to get the spacecraft moving exactly, within a few meters per second of the comet's speed, so that it's able to go into orbit around it. And this is the Comet rendezvous, which was it was a series of burns in the middle of 2014. And then the final part of the mission is really the events, the mapping of the comet. So you arrive at this comet, you don't know what it looks like before you get there. You've no idea exactly how big it is, what sort of shape it is, what the surface is likely to be, how are you going to land on something? Is it going to be hard? Is it going to be soft? What density is it going to be? So there was a big effort on mapping the comet and then going into orbit around it very carefully. Don't want to get too close to begin with, because you don't want to hit the surface, obviously, but you also don't want to, you want to arrive before it gets too active so that you can see things rather than see a load of dust coming up from the surface. So this was deliberately early enough that before the comet got active, before it got too close to the sun. And then in November 2014, there's a big debate about where to put the lander down on the surface, which I'll talk briefly about, but I won't go into the full saga. That could be a talk all on its own. And then the rest of the mission is really with the scientific experiments on board the orbiting spacecraft, flying alongside the comet and around it as it gets closer on the sun, and step by step moving further back from the comet as it gets more active. I think there was a couple of occasions when the spacecraft got blinded by the amount of the star trackers were looking at all this dust and thinking, oh, there's a new galaxy over there. And they got totally confused. And the spacecraft put itself into what's called safe mode, when it basically shuts everything down apart from its vital equipment on board. So it shuts all the experiments off and says, I need to speak to the ground and work out where on earth I am. So this happened a couple of times. So the spacecraft controllers had to get a little bit more cautious in terms of how close they could go to this comet when it was very active. Now, the end of the mission was supposed to be at about 2 astronomical units. So you go past the perihelion point and you're on your way back out for the next lap. But Rosetta was never going to be able to do all of that. Don't forget, it needed to go into sleep when it was at aphelion. So it was never going to be able to follow a comet all the way around a complete orbit. And when the comet's not active, it's not so interesting anyway. But they did actually choose to extend the mission till September 2016, which continued because it was a bit more active than they were expecting. So they were still able to make interesting measurements after the closest approach. And then they had the great idea of, instead of leaving Rosetta to orbit alongside the comet for the rest of eternity, they thought, well, we'll do our bit for space debris and we'll put it safely down on the surface of the comet. So that's what happened. Never designed to do that. And it obviously wasn't something it survived. But they actually put in September 2016, they actually had a soft crash of the spacecraft at the end of the mission onto the surface of the comet. So that was how it ended up. But that wasn't the plan back in the mid to late 90s. So let's talk about, you can see, sorry, I'll have a drink of water. Right. So you can see we've done a few laps around the sun in order to get out to the comet. What does that mean? So on this diagram, I'll explain what's going on. So on the left-hand scale, ignore the two curves for the moment. On the left-hand scale, you've got basically astronomical units from 0 to 6. The furthest point where the top of that blue wiggle is about 6 astronomical units. And on the bottom, you've got time. So you've got the 11 years, essentially, from 2004 to 2015, with those ticks at about every 6 months. So what are these curves? So the first one, let's talk about probably the first one is the pink one, Hopefully you can see pink, and the other one's dark blue, I think. The pink one is the distance between the sun and the spacecraft. So you can see it starts off at about 1 astronomical unit. There's a bit of a wiggle. It comes back to 1 when it has the first Earth flyby, goes out a bit, almost up to 2 astronomical units from the sun, back towards the Earth, back to 1 astronomical unit, and then round again. Has its first encounter through the asteroid flyby at about this point here. Has its final Earth flyby when it comes back to 1 astronomical unit, and then it has its long sweep out to just over 5 astronomical units. This is when it's matching the orbit of the comet, and then it comes in at the end. So why are we interested in that? Well, and if you think about this, for an Earth orbiting spacecraft, all you see would be a flat line at 1 astronomical unit. Life would be simple. Spacecraft would be straightforward. So the pink line is the problem. The problem that gives us is the solar panels and the thermal subsystem, because it has to cope with these enormous distances or variation in distances from the sun, which is how it's generating its power, and how it's controlling its how it's controlling its temperature inside the spacecraft. Because having the sun at 1 astronomical unit is very different to having it at 5 astronomical units. So this has big implications for the power, the solar array, and the thermal side. Now, the dark blue line is the distance between the Earth and the spacecraft. So you can see it starts off at 0 because the spacecraft is sitting there on its launcher on the surface of the Earth, and so on. You can see it flies away from the Earth, comes back. You have the Earth flybys. You can see at these points again, the 3 Earth flybys, and then it does its long swing out. Now, what's this wiggle on the curve out here? Well, this is the spacecraft being a long way from the sun and a long way from the Earth, and this is the Earth going around the sun as viewed by the spacecraft. So that is the Earth going around the sun when you're a long way out, and you're spending a long time there, years. And what's the implications of that? Well, and you can see it gets over 6 astronomical units from the sun. The implications for that are the communications. You've got to communicate with something that's 6 astronomical units away, which is a long way. So, and we'll talk about the speed of light in a moment, but it also makes a difference in terms of the antenna size, and that's why this spacecraft has an enormous high gain antenna. That's over 2 meters across in diameter. Sorry, I should explain. This is my friend Buzz, and if he's a 5'3" astronaut, he's about the right scale. This is a 20th scale model. Sorry, Buzz, I forgot all about you. So 5'3" is probably a good size for an astronaut, actually. I mean, they're a bit taller these days, but the early ones. Okay, so hopefully you've got some of the things off that. Oh, another graph. Okay, so the blue and the green wiggles on this one are basically the curves we've just been talking about. So you only need to concentrate on the red one here. Now this is the right-hand scale, not the left-hand scale. And you've got time across the bottom here. And essentially you want to concentrate on the red one. So what's happening here is this is a plot of the angle. If you've got imagine your eye is on the spacecraft and you're looking at the sun and you're looking at the Earth, how far apart are they in terms of angle? And so this is what is plotted here, the sun, spacecraft, Earth angle. And you can see the 3 Earth flybys quite distinctly here, because that's these sharp spikes when the spacecraft whizzes past the Earth, and the angle changes very quickly because the Earth and the sun are moving relative to each other as viewed by the spacecraft. So what's the significance of this? So this is really telling you about the field of view of your antennas. So you can see at the end of the mission, hereabouts, you can see the angles between the sun and the Earth, because you're a long way out. We're only about within 15 degrees of each other, which makes it very nice if you're a medium gain antenna with a beam width of about 15 degrees. So you can literally point your spacecraft at the sun and know that the Earth's going to be in view of your antenna. That was one of the attractive things of having a medium gain antenna on board that could allow that contact. The other interesting thing about this is that where the angle comes to 0, it means you've got the sun, the spacecraft, and the Earth all in one line. Okay, so this is called a conjunction, a solar conjunction, and that has a number of implications. One of which is that you can't really communicate with the spacecraft from the Earth because you've either got the sun in between you, or the spacecraft has got the sun in its view and can't hear the signal from the Earth because of all the noise from the sun. And so here you can actually see this is the Earth going around the sun at this point, and you can see there's a conjunction every 6 months because, of course, the Earth is either behind the sun or in front of the sun as it goes around, as viewed from the spacecraft's point of view. So this was an important issue for the the communications on board the satellite. Right. So how long? Speed of light. This is an important factor because we've got enormous distances and our radio signals go at the speed of light. So to get out to 6.5 astronomical units and back from the Earth, and we're a little bit further than that at one point. It's over 100 minutes. So you can see it's getting a signal out and back is going to take a long time, and that's even assuming it responds straight away. The computer might need a few seconds. And some of the events in the mission were occurring, and the lander delivery, for instance, was at 3 astronomical units. So that's over 50 minutes. So you can't have a conversation with a spacecraft about this. It's time to let it go. It's got to be told you need to do it on this time, this attitude. That's it. And don't phone me up with the wrong answer. You've got to do it. Make sure it happens. Make it so. The rendezvous maneuver was at about 4 astronomical units. That's over an hour away. So that big maneuver, it was a series of maneuvers, but those maneuvers had to be done precisely. Asteroid flybys were at about 2.5 astronomical units. Those were over 40 minutes away. So it all had to be done with a certain amount of autonomy on board the satellite. So this isn't a problem if you're in orbit around the Earth, because you're only a second away. So I said I'd tell you something about deep space hibernations. This is when the spacecraft was furthest from the sun. And the spacecraft was operated in a completely different way at this point. Normally, the spacecraft is sitting there, it's not spinning. It knows where it's looking, at the comet or at the Earth or at an asteroid. And it's in what we call 3-axis control. So it's not rotating, it's pointing at a fixed attitude in space. And it's using its control system on board, reaction wheels, thrusters, etc., to do that. For the hibernation, because you needed to turn basically all the electronics on board, apart from the heaters were the most important thing, and the computer. But most of the power was was provided to the heaters because it was so cold, a long way from the sun. And it was put into a passive spin. So it's spinning end to end like this, around this axis, as it were, at about 4 degrees per second. So that's 90 seconds for a complete rotation. So quite slowly, but that gave it enough gyroscopic stability to leave it like that for 2 years, and it's still pointing in the same direction 2 years later. So by doing that, we were able to power off a lot of the electronics, leave the spacecraft in a safe position, and be able to not lose too much sleep about finding it later on. Okay, some pictures now of the real spacecraft, which I'll tell you a little bit about. So this was being prepared for launch, probably for the first launch. So you can see on the right-hand one the size of a human. I'm not sure how big that guy is, but he's probably 6 foot, something like that. And the spacecraft is 2.6 meters tall. And just about in the middle of that black face, you can see the lander with its legs folded up. It's a bit hard to see, but I'll show you some pictures of the lander later. But that's it being lifted and prepared, ready for the mating with the top of the Ariane 5. On the left-hand side, you can see what looks like a spaceman, but he isn't. He's actually doing a very dangerous job, which is fueling the spacecraft before launch. And I'll talk a bit about the propulsion system in a moment, but you've got some very noxious chemicals, and that's why he's suited up, so that there's no chance he's going to breathe any of those in. You can see you've got a good view of the high gain antenna on that view on the left-hand side. The panels you can see are the solar panels folded up on the side of the spacecraft there for launch, as they have to be, because that wouldn't fit inside a rocket. Right, here we have an exploded diagram of the spacecraft. And I won't go through every detail here, and you can't read it all anyway, but I'll just point out some of the main features. So you can see you've got a central cylinder there, and then panels around the outside. But dominating the size of this thing are the two solar wings. You know, you've got I think it's over 60 square meters of solar panel, which generates about 400 watts at aphelion and about 8,000 watts when it's close to the Earth, which you can't do anything with that power. You don't want it. But you can see the solar arrays were a significant thing to accommodate. The large high gain antenna is another big thing to accommodate in the spacecraft configuration. Now, inside the central cylinder, you can see what looks like a sort of green blob there, and that's the top of one of the fuel tanks. There's two fuel tanks inside there, and they're each about a cubic meter, so quite a large tank. And these carry the fuel and the oxidizer, and they constitute about half the weight of the spacecraft at launch is the fuel and the oxidizer. The orange bits on the top panel are the scientific experiments, which are all on that face, the equivalent of this face on this model, which all look at the comets, and some of them have co-alignment requirements, so you need to know where one experiment is looking relative to another. If there's any mechanical engineers here, then the panels are made out of aluminium honeycomb, if you're interested. So the main characteristics, so the wet mass, this is the mass of the dry spacecraft with all the fuel and the oxidizer on board, was just over 3 tons at launch. You know, and most of that, as you can see there, is the fuel and oxidizer, 1,718 kilos. The dry mass was about 1,300 kilos. Most of that was the platform and the avionics, and the big items were the structure itself, and the solar array was about 170 kilos between those two wings. There's about 192 kilograms of science experiments on the orbiter, on that face, and the lander itself was about 110 kilos. And I'll talk a bit about the experiments on the lander in a moment. So the solar array was about 32 meters tip to tip, so quite a big thing. So I think we talked about most of these things, so maybe I'll skip over this one in view of time marching on. I think we've mentioned most of those things. Maybe the other thing we haven't talked about is the large delta V maneuvers near the end of the mission. So for a normal spacecraft, you do your maneuvers, get into your final orbit, and then do your mission, whatever it is, communicating with the Earth or whatever. For Rosetta, it was the other way around. The spacecraft took 10 years to get there, and then it does some big maneuvers right near the end. So this is very unusual for a propulsion system. And the other thing we haven't mentioned perhaps is the small delta V maneuver. So the precise maneuvers at the Comet, and they were millimeters per second, which is pretty unusual because the gravity is so low on the Comet. It's like everything happening in slow motion. Instead of going around, you know, if you have the spacecraft going around the Earth, it takes about 100 minutes, depending exactly how high it is. Going around the Comet, it's in slow motion. It takes a few weeks, you know, compared to 100 minutes. It's a completely different world. Okay, maybe I'll just pick out the flexible operations, the third bullet there. So I said we didn't know what we were going to find when we get there. So by definition, we have to be able to deal with whatever we find. So we have to be able to program the spacecraft and the science experiments on board so that we maximize the chances that we find when we get there. The solar array, this is worth, I mentioned some of the problems with the huge change in distances. And what goes with that is a huge change in temperature. So the solar panel itself will be much colder when it's furthest away from the sun, minus 130 degrees centigrade compared to sort of 50 degrees if it's near the Earth. So what does this mean? So one of the things it meant was there was a special development for the solar cells because they had to. This is the first spacecraft that's taken a solar panel out to Jupiter's distance. NASA take radiothermal isotope generators, so they don't take solar panels out to that distance. And it's all very green and eco, but you have to have the technology to go with it to be able to do it. So ESA had a special development of low intensity, low temperature cells. That's what the LILT means, low intensity, low temperature. To get these solar cells to work over these huge ranges of illumination level and temperature. And then the final thing was the MPPT, which stands for Maximum Power Point Tracking. And this was, again, this is technology that was developed and used for the first time on this spacecraft. And this was to get the most out of the solar panels. Now, why is that important? Well, in the upper right-hand corner, you can see a graph of current on the vertical axis and voltage on the horizontal axis. And this shape of curve, this IV curve with this particular shape is you'll find on any solar technology. And the knee, where you've got a maximum of the current and plus times the voltage is the power. So the maximum power point is on that knee of the curve. When you see P max identified. So what the maximum power point tracker does is deal with the situation when, here we go. So when the array gets hotter than that example curve I've given you, the current will go up, but the voltage will start to reduce, and the knee, the maximum power point, will be at a different voltage. So to get the most out of the array, you need to deal with these movements of the IV curve. If it gets cold, it does that. The maximum power goes out to a higher voltage. So the maximum power point tracker is electronics inside the spacecraft that is getting the most out of the solar array and the conditions it's operating under. So this technology was, absolutely needed in order to make the mission work. One of the other things we had problems with was the thermal control. So the distance from the sun was changing enormously. If you've got a normal spacecraft, you basically tune it so that you have radiators on the surface of the spacecraft that allow you to lose the amount of heat you need to lose to keep a balance and keep the electronics inside the spacecraft at room temperature or thereabouts. So what we had to do here was deal with the situation when the spacecraft is at the Earth's distance from the sun, 1 astronomical unit, and it needs to have needs to be able to lose heat at that distance. But when it's at 5 astronomical units, it's out in the deepest space. You can't afford to have these radiators open because you'd just be losing so much heat out of the radiators. So these louvers were an idea to close off the radiators when the spacecraft is cold and reduce the amount of heat. And they're really, really clever devices. They're like bimetallic strips. They're called louvers, in honor of the French, of course. And they close off the surface so that it reduces the emittance from that part of the spacecraft. You can see the rest of the spacecraft is black and it's got 20 layers of insulation, so that you've got no heat coming, virtually no heat coming through the rest of it. It's just coming through these areas. So why was that necessary? Well, if we hadn't had those louvers, instead of about 300 watts of heater power, I would have needed another 700 watts of heater power, which, you know, would have meant the array would be, well, about 3 times that. So it wasn't practical not to solve this problem in terms of the power implications. The propulsion system, right? I'm not going to. You'll be pleased to know I'm not going to describe the propulsion system in detail. I'll just point out these are the 2 fuel tanks you see here: the monomethyl hydrazine and the nitrogen tetroxide. That's the oxidizer, which are the 2 chemicals you mix together to make the ignition and the thrust. At the bottom, you can see 24 10-Newton thrusters. Now, one of the uncertainties for Rosetta was, how do we know how much fuel we've got left? Because we've got these various maneuvers we're doing at different points in the mission, and a lot of them towards the end. And one of the ways we dealt with that was to periodically heat the tanks, the 2 fuel tanks, the fuel and the oxidizer tank, with a known amount of electrical heater power, and then measure the temperature rise. And from that, knowing the specific heat capacity of the 2 chemicals, you could work out roughly how many kilos of fuel you had left. So this was called thermal gauging. So this was a technique that wasn't developed for this mission in the first case. It had just been coming in on telecommunication satellites at that time. So we were able to ride on the back of that development and use it. But the first time on an interplanetary mission. One of the other things I should say is, although we've got 24 Newton thrusters, we've got no main engine. Now, by a main engine, I mean an engine of, say, 400 newtons, which you'd normally have for these large maneuvers that you do on a spacecraft like this. Now, the reason we didn't choose to have one is that the maneuvers we're doing are rather unusual in that they're not very time critical. So whereas if you've got a spacecraft going around the Earth and you need to change orbit, you need to do it reasonably precisely within seconds. Whereas the maneuvers we're doing with Rosetta are taking place in deep space, and you know, a few days doesn't matter in terms of time criticality. So we were able to do the burns using 4 10-Newton thrusters, so you know, a tenth of the thruster power, but have the burn of several hours. So the spacecraft could, you know, move slowly, but it didn't make a difference to the efficiency because it was being done a long way from the Earth or from the Sun. So that was so that's an unusual thing. You know, if you look at other interplanetary spacecraft, if they're going to orbit around Mars or Jupiter or wherever, they will have a main engine because they need to do it precisely at a particular point in time. Right, and we'll move on. Telecommunications. So we talked about the high gain antenna. What shall I talk about here? Yeah, the high gain antenna had to move in 2 axes. So, and you can see it on this model. To allow the antenna to be pointed at the Earth and the spacecraft and the scientific payload to be pointed at the comet, wherever it was. So this was, you know, a complication for the design of the high gain antenna and the radio frequency connections to it, you know, through a rotating joint. The other thing the project had to do on the ground was it had to build a new ground station in Perth. So this wasn't part of the spacecraft contract, but the European Space Agency and the Australian Space Office, I think it was then, had to build a 35-meter ground antenna. And that was because there wasn't enough capacity on the ground without really relying on NASA, which good Europeans don't want to rely too much on the Americans on, no more than we have to. The transmit power is only 28 watts, so you've got these enormous distances, but you're limited as to how much power you can transmit, and that's basically why you want to have a very big antenna with a lot of gain, so that you can get a signal back to the Earth a long way away. A quick word about the avionics. This wasn't really part of the spacecraft I had to look after, but we talked about the autonomy earlier on. And these CDMUs, that's Command and Data Management Unit. This is the computer. There were two of them, and they had two processors within each one. And this is where the timer function was that triggered the wake up from hibernation. The avionics also included, most importantly, the navigation cameras, which we used to look for the comet in the lead up to the rendezvous. So where is it? We know roughly where it's supposed to be, but where exactly is it? And when the spacecraft flew past the asteroids, the navigation cameras we used to locate where the asteroid was in its field of view and control the spacecraft, turning as it flew past. And then finally, once you were in orbit around the comet, they were used for the mapping of the surface of the comet. And I'll show you a picture of that in a moment. So next section, I've been talking for what, 50 minutes so far, I think. So I need to pick up the pace a bit. So Philae, the Rosetta lander. So that was named after a particular obelisk which was found in 1815, Waterloo. And it's in the gardens of a house called Kingston Lacey down in Dorset. If you ever want to go and have a look at it, there it is. I'm not sure exactly how much hieroglyphs it's got on it, but anyway, this is what the lander was named after, and this is where the UK, the Ptolemy experiment that the UK did came involved. So this is a picture of the lander. You can see it's about the size of a large microwave, small washing machine. It's on a handling frame there, and you can see it's got its 3 legs deployed. So that gives you some idea of the size of it. 110 kilograms, I said earlier. And this was a European lander. It had some experiments from NASA on board it as well as the UK experiment and experiments from around Europe. It was led by the German Space Agency and with the support of the French Space Agency. So here we are. This is the UK's experiment, and you can see it's about the size of a shoebox in terms of volume. You can see on the right there with one of the Open University scientists. On the left-hand side there. Inside the black box is the electronics, so it doesn't look very interesting. The chemistry stuff is more interesting, which is the bit that you can see exposed. It's basically a gas chromatograph, and it's measuring small species, small molecules, quite often charged molecules, in a mass spectrometer. The chap on the lower right is Colin Pillinger of Beagle 2 fame. Beagle 2 was his second science experiment in space. Ptolemy was his first. And when I first went to the Open University and when I first got involved in the project, they showed me the equipment they were trying to put in space, the ground-based equipment, and it took up about 2 tables this size and ended up inside that shoebox, which I think is pretty impressive. So here we are. We get from spaghetti to an assembled scientific instrument just like that. And in that picture is about 60 pipes and about 200 wires, just to give you some idea. So it's an amazing bit of miniaturization. Right. This is the lander, the body and you can see some of the internals, and you can see on the right there, this is the Ptolemy experiment mounted on a sidewall there, being checked out as part of the integration. Right, I'm on the last few slides. So I want to remember what it was like in 2014. In January, the spacecraft woke up. It then, over the next few months, it started to look around for the comet, which had been a very dim blob up until that point. And then this amazing shape emerged, and you can see here a little bit, and it resembles effectively a rubber duck in terms of the shape of it. In terms of it's what's called a contact binary. So a long time ago, presumably near the start of the solar system formation, two of these bits came together at quite a low velocity and ended up being stuck together, because you wouldn't naturally get a shape like that. So this is what was discovered in the middle of in July, in a couple of weeks, as the spacecraft got, instead of thousands of kilometers away, it got closer and closer, and this shape emerged from the images of the cameras. And it was quite an amazing moment to, because it's not that uncommon to find contact binaries like this, but it wasn't expected. And it explains why the light curve is a bit interesting. So having got that shape, you then have to work out where you want to put your lander down on the surface. And this is what exercised those few months from August, September time in 2014, before choosing the land, or doing the landing in November. So this was a very very busy time for the scientists. From the global mapping, and you can see it's a duck, isn't it? It's a duck. This is a model that's been put together from the images. So from each of the images from the camera, you can put together a detailed shape of the comet. So as the spacecraft and the comet got closer to the sun, you got these sort of fantastic images. So the duck's neck there is obviously a very good source of violet gas coming out there. And there are hundreds of these, well, thousands of these images that you can see. I just picked out some of them here just to give you an idea of what it was like. This is an interesting one. So this image is from one of the science cameras with the narrowest field of view, and the size of the image is about 228 meters in each direction. So that's a 228 meters by 228 meters piece on the surface of the comet, and the spacecraft is about, let me just check, it's about 6 kilometers above the surface. Yeah, 6 kilometers. So 6 kilometers above the surface of this thing that's rotating in space. And you can see at the bottom, that is the shadow of the spacecraft on the surface of the comet, which is quite an amazing thing. It's about 20 meters by 50 meters. Some images from February 2015 when it's getting more and more active as it gets closer to the sun, and you can see these different jets, and all of this stuff is being measured in terms of what's in these jets, being detected on the orbiter. This is a shot of the neck of the duck, and you can see some of the features here. There's like cliffs, and you can see these strange what look like terraces, and sunken bits of the surface. All sorts of interesting things going on. This graphic is a summary of some of the main things. So you can see 3 or 4 kilometers in terms of diameter. The density was an interesting one. It was a bit lower than we were expecting, but it's 470 kilograms per meter cubed. So that's about half the density of water. So if you put this thing on the surface of the ocean, it would float, sort of. So that's a lot lower than you'd think, perhaps. I mean, it looks quite rocky, but it's really very porous. Rotation period of around 12 hours, and then it rotates about particular axes. Right, and I'm going to talk about the DH ratio in a moment. That's deuterium to hydrogen. And the temperature, is quite cold on the surface. Average albedo 6%, so that explains why it's quite dim when you're viewing it out in deep space. It's not reflecting much sunlight. This gives you the size of the duck compared to Manhattan City. So if you're wondering what does a few kilometers look like, there you are. This was some American graphic artist that came out with this one, but it was quite neat. So it's my last slide. So at the bottom, I've got the URL for the where you can find the images if you're interested to have a look. There are literally thousands there. So one of the things scientists have talked about quite a long time is where did the water come from that we find on Earth? Because you don't see it on other planets so far. And does it come from comets? Does it come from asteroids? Does it appear from somewhere else, from the internals of the Earth? When you look at the Earth from space, you see the blue planet, and if you look at the Pacific in particular, you see hardly any land. If you look at the Pacific, it's all the Pacific Ocean. But when you measure how much water is on the surface of water there is on Earth, it's a surprisingly low percentage. It's 0.02%, the mass of the water on Earth compared to the mass of the Earth. So there's quite a small proportion. It's obviously all on the surface or on the top layer, but it's quite a small amount of water. So compared to the mass of the Earth, it's quite possible that it could come from outside the Earth, from an asteroid or a number of comets or a number of asteroids. But one of the things they looked at was the isotopic ratios, because this is an indicator of the ratio of normal hydrogen to deuterium for the water on the comet compared to the water on Earth, and it's a much higher percentage of deuterium on the comet. So it doesn't look like, if this comet is typical of comets, it doesn't look like comets are the explanation, or certainly the only explanation of where this has come from. I think I'll probably stop at this point. I mean, I think, or maybe the other one other thing to mention: amino acids, glycine. That's one of the things they found, and other complex organics. But that's probably the most complex one that stood out in my reading of what's been going on. And the water and ice on the comet, you can see there is a cycle where it sublimates during the day, into vapor, and then freezes again at night. So there's like a water cycle going on, which was observed. Some other numbers: 200 tons of material they could see being ejected in some of the most violent jets in the space of a few minutes. I mean, 200 tons sounds a lot, but your comet mass was, remind me, 10 to the 13 kilos. So you can lose a few tons before you're worried about it. Anyway, that was a whistle-stop tour around Rosetta. So I'm going to stop at that point and invite you to ask any questions.
It looks like two bodies are colliding against each other. Is that correct?
I think that's almost certainly what's happening. It's called a contact binary, and it happens in planets and planetesimals, even in stars. I think you'll see stars will get close together, and their atmospheres will touch, and then they'll move in a joined up way. So yes.
You've got heaters on there. Presumably you've got battery packs as well. What was the battery technology with the heaters to keep them going?
Yes, lithium batteries. Yeah, they did. The temperature of the batteries had to be controlled because, yeah, not good getting cold. Same as on Earth. Yeah, there were temperature sensors, of course, and but a lot of the time, when all the electronics was off, it was all thermostatically controlled heaters. Yeah, with redundant thermostats. But yeah.
Were you expecting to find the organic molecules?
Yeah, I think people. I mean, I'm not a commentary scientist, but I have here with me, courtesy of the Open University, a postcard which is impregnated with the smells of the comet. So feel free to come and have a whiff. Yeah, I left it in the bag to keep it. Well, I think you'll recognise hydrogen sulfide certainly.
So the comets become more active when it gets near the sun. Is that just due to the heat warming?
Yeah, yeah. I mean, primarily the heat from the sun, the whole thing gets warmer. Yeah, and then it cools down as it gets further away and becomes less active.
Anybody observed the comet getting a lot smaller because of the tail?
No, I don't think so. Not yet. I mean, if we carry on monitoring it for a long time, I guess we might discern some difference. But you know, it's 10 to the 13 kilos, and I don't know how much mass it loses per orbit, but it's probably a very small fraction.
But the Thales Comet was very disappointing in its last pass because we have lost quite a lot of the volatiles in previous passes.
Okay, I bow to your experience.
And not just the period that changed, the rotation period of the planet over the few months.
Yes. Well, I guess it's just the coincidence of the jets with the rotation direction. You know, some jets are going to make it speed up, and some make it slow down. But you know, it all depends on how much mass is in those jets and exactly what angle they are. You know, compared to the rotation axis.
The early days of looking at comets, you know, you've seen a comet, but isn't that always kind of a 5 years to come around again? Or is it just a moving sort of mass that they observed? You know?
Well,
have they ever been able to work out anything about the orbit going back 100 years ago?
well, the 67P was only discovered in 1969, so it's only done a few orbits since then. You know, 6.5 years. But I guess they're, you know, by ground measurements, you see this faint object moving across the sky, you know, relative to the background stars. It's very faint, so you've got a job detecting it, and then you've got to measure it over a period of time to work out what its orbit is, and that gradually gets more and more accurate, I guess, as time goes on.
After the propeller, did it actually, was it specially developed because of the length of the mission to stop degrading, wasn't it?
No, no, that monomethyl hydrazine and nitrogen tetroxide are a fairly standard spacecraft propellant set. You do have to take, I mean, and 11 years isn't that long a time. I mean, it is going those sort of distances, but you know, for a telecommunications spacecraft, you know, 10 years, 15 years in orbit around the Earth. I mean, most of it will be used at the start, but there will be bits used potentially later, you know, for station keeping perhaps. So there's no incompatibility with the timescales.
The spacecraft was to become sort of involved with one of the jets. We've been pushed away, you know,
Yeah,
to
I,
navigate away from them.
by the time it was at that stage, the spacecraft was, like 50 kilometers away, or even 100 kilometers away. So they were being very cautious about backing off as the comet became more active.
Another question, you mentioned, I think the transmit power was 28 watts.
Yeah,
What kind of frequency band is?
this is X band. Yeah, so 8 gigahertz thereabouts. And it's tens of kilobits per second in terms of data rate.
Well, yeah, and those
Yeah.
frequencies.
Yeah.
Data.
So if it looks like a duck and it spins, it's probably a comet. Thank you very much. That's an excellent talk.